And the second speaker is Professor Nick Andersen from Brigham Young University, USA. And he received his doctorate under Professor Scott Algram, and starting his research from 2016 onwards from the University of Illinois. And his main interest is algebraic part of the automorphic forms and its close connection with number fields of at least degree 2 and hyperbolic geometry, class numbers, L function, and additive number theory. And I welcome him for this second session. And now you are.
Thank you. Can you hear me? I'm really glad to be here, and I'm appreciative of the invitation to come and give 5 lectures, which is so much. But thank you in advance for paying attention to me for that long. So I want to treat this sort of like a classroom. Please just ask questions, interrupt me at any time. If you have any questions about anything that I say or you want any clarification about anything, just feel free to ask the question. And don't wait until the end for questions. I've already received a directive to write bigger than that, so I'm going to. But if you want me to write even bigger, especially if you're in the back, just let me know. Okay, so this first lecture is going to be maybe the boring one. I'm sort of giving an introduction to the basic definitions and basic properties of the objects that we're interested in. There's not going to be a lot of really rich or interesting things going on until later, but we have to set the stage and we have to be all on the same page, I think. So let's just do it. Let's start by picking a group, gamma, which is going to be a subgroup of SL2Z. And let's say it's a finite index subgroup, a congruent subgroup even. And for the purposes of all of my talks, these groups are always going to be of one of the following 2 forms. So gamma will either be gamma 0 of n or gamma 1 of n. And these groups, the matrices in these groups, in gamma 0 of n, all of the matrices are congruent to anything, 0, anything, mod n. And all of the matrices in this group are congruent to 1, anything, 0, 1, mod n. Okay, and these are the usual standard congruent subgroups of SL2Z that we're going to work with. We're also going to fix a weight, k, which if we wanted to, we could just say k was any real number or any complex number even. But for the purposes of my lectures, I'm going to say that k is half of an integer. So either an integer or an integer plus a half. All of the most interesting examples are in these weights, and so this is probably good for us. So the fundamental property of a modular form, so the fundamental property that we've already seen is that the modular form should transform according to the elements of this group. So you should get something like f of gamma z is equal to cz plus d to the k. And you know what? I said I was going to use tau instead of z, and that's going to really throw me off, but I'm going to try. So I'm going to use tau instead of z, f of tau. And here I'm writing gamma is ABCD. And it's in the group gamma. And this should hold for every gamma in big gamma. Okay? This is the fundamental property of a modular form. And so everything we talk about is going to satisfy some property that looks like this. But there's one kind of picky frustration here that we're going to have to deal with, and so we might as well deal with it right off the bat, which is that if if minus the identity is in the group, which it is every time we're looking at gamma 0n, it certainly is. If minus the identity is in the group, then if you plug in minus the identity into here, well, what you get is f of tau equals, let's see, minus 1 to the k f of tau. And this is bad unless k is an even integer. So this means that k had better be an even integer, or f is just the zero function, which I don't think we're particularly interested in. So if we want k to be half an integer or an odd integer or something, we need to do something a little bit more general. And so let's do that. So what we're going to do is change this fundamental property a little bit. We're going to introduce another factor here. So what we'll do is we'll introduce what's called a multiplier system. And I'll call that nu, and it's going to be a function from gamma to the complex numbers, and let's say the non-zero complex numbers. And what I want is for f of gamma tau to equal nu of gamma c tau plus d to the k f of tau for all gamma. So this is going to imagine this is it's going to end up being a root of unity. So this is some root of unity that's going to just kind of twist things around a little bit. And let's see what has to happen in order for this to be consistent with itself. So for consistency, well, let's compute f of gamma 1, gamma 2, tau in two different ways. So in the one hand, we can think of gamma 1, gamma 2 as being a single matrix. And so we can use this property here to say this is nu of gamma 1, gamma 2. Oh, I did not leave myself enough room. Yeah, let's fix that. And also I need to do one more thing. So let's let j of gamma tau be the function c tau plus d. So it just reads off the cd from the bottom row of gamma and then puts in the tau. And so, okay, let's try that again. So f of gamma 1, gamma 2, tau, on the one hand, it should be nu of gamma 1, gamma 2, j of gamma 1, gamma 2, tau to the k. That's your c tau plus d to the k, and then f of tau. Okay? So that's if we think of gamma 1, gamma 2 as a single matrix. But now if we think of it as two matrices, let's compute this using just gamma 1. So what we should get is nu of gamma 1, j of, let's see, gamma 1, gamma 2 tau to the k, f of gamma 2 tau. That's just using the gamma 1. And now I'm going to do it again with gamma 2. I should get nu of gamma 1, nu of gamma 2, and then j of gamma 1, gamma 2 tau to the k, and then j of gamma 2 tau to the k f of tau. Okay, and so since there's an f of tau on both sides, if f of tau is not 0, we will divide by it, and so we're going to get some kind of relation that needs to hold. So what it says is that nu of gamma 1, gamma 2 should equal nu of gamma 1 times nu of gamma 2 times something else, which I'll call omega of gamma 1, gamma 2, where omega of gamma 1, gamma 2 is, let's see, well, what does it have to be? It's going to have to be j of gamma 1, gamma 2 tau to the k, j of gamma 2 tau to the k over j of gamma 1, gamma 2 tau to the k. And you can check, there's a little bit to do here, but you can check that this actually is invariant under tau. You can plug in any tau you want, and you'll get the same thing. So you might as well plug in tau equals I, for example. And this will just be some number, okay? You can think of it as sort of measuring, as sort of fixing what might happen if k was, for example, 1/2. And what we're doing is basically choosing a branch of the square root function, of the complex square root function. And different weird things that happen with branch cuts can cause some issues. And what this is doing is sort of measuring those problems. And so this factor omega is sort of fixing that. And it's making it so that we can talk about things that are more interesting than just k being twice an integer. And we can think about k being half an integer, for example. So this is what's called a multiplier system, this nu. And so if k is half an integer, then it turns out that this omega gamma 1 gamma 2, well, it's not too hard to see that if you square this whole thing, it's not too hard to compute algebraically that this just has to be 1. And so this must be plus or minus 1. And basically this is just measuring the choice of, or the differences between the choices of the branch of the square root function. So you can think of nu as almost a homomorphism of this group gamma, but it's not quite, because it'll be off by maybe a minus sign when you try to factor. Okay, good so far? All right, so there are a couple of examples of these, just so that we can be really concrete here. So if k is an even integer, then what we get is nu of gamma 1. Well, actually, if k is an integer at all, what we get is nu of gamma 1 gamma 2 is equal to nu of gamma 1 nu of gamma 2. And so we really are just looking for a homomorphism, or a character of this group. And so we can, as an example, we can take nu of gamma to be, let's pick, like, say, a Dirichlet character. So maybe a Dirichlet character chi, and we'll just plug in the lower right entry of gamma, d. And so I would be a Dirichlet character mod n. Okay, and I'm probably not going to talk about too many examples with Dirichlet characters, and so if I don't mention this, then we'll just assume that chi is the trivial character mod n, if I don't mention it in the notation. Okay, so that's the integer case. Oh, and I guess we can say a little bit more about this. We need to have that chi of minus 1 is minus 1 to the k. So if k is even, then you need an even character. If k is odd, you need an odd character. Now, if k is half an integer, and there are lots of interesting examples here, but I'm going to mention 2. So here's some examples. The first one is called the theta multiplier. And it's associated to the usual theta function. Theta of tau is some n in z of q to the n squared. Here q is e to the 2 pi I tau. So that's the usual theta function. So the theta multiplier is the multiplier system for this theta function, which is a weight 1/2 modular form. And we can write it down explicitly. Nu of gamma is, well, to look at my notes here, can be C on D, epsilon D to the minus 2k. So here C on D, this is just the Legendre symbol, extended to be able to handle all of the inputs that you want to put into it. So the usual Legendre symbol, and then epsilon D it's the sign of the Gauss sum. So it's 1 if D is congruent to 1 mod 4, and it's I if D is congruent to 3 mod 4. And so that's an explicit formula here. And if we're going to use the theta multiplier, we will be assuming that 4 divides n. So this only makes sense if n is divisible by 4. And so therefore C is also divisible by 4. Okay, so that's the theta multiplier. And again, if I don't say anything about what multiplier system we're using, and if k is half an integer, I'm going to be assuming by default that we're using the theta multiplier. And you can also include Dirichlet characters to this as well. You could just multiply the theta multiplier by a Dirichlet character and get some other interesting things. So another one that's interesting is the eta multiplier. And this is associated to the Dedekind eta function, which is q to the 1/24th product n equals 1 to infinity of 1 minus q to the n. And you'll notice this is the 24th root of the delta function that showed up in Professor Murty's talk. And the inverse of this is the generating function for partitions. And we'll talk a lot more about that later, not so much today. But this is a multiplier on SL2Z, and therefore every congruent subgroup of SL2Z. And I'm not going to give you the definition of it because, to be honest, it wouldn't really help anything. It's just sort of complicated, and I'm not going to write it down. But you can look at it. So we might talk about the eta multiplier maybe on Wednesday or Thursday, but not today. Okay, how are we doing so far? Yeah? Okay, good. Yeah, so theta is a modular form of weight 1/2 on gamma 0, 4. And so if you want this to be a multiplier system, it has to be a subgroup of gamma 0, 4. So we need to have 4 to divide n. Yeah. Okay, so I'll erase for a minute. And if you think of any questions while I'm erasing, you can say them. Pretty. You're talking about this J? Oh, omega as a cocycle. Yeah. Mm-hmm. Sure. There are things that you can do there. Yeah, that's not something I've thought about a lot, but yes, absolutely. I believe there are some interesting papers like that. Let's see. Where was I reading about that? I'll have to think about it, but I could tell you later. All right. Okay, so it will be convenient to define one more thing before I get into modular forms. So I'm going to define, shouldn't talk in the corner. I'll define the slash operator. So this acts on any function, any complex function. So f slash k of gamma is going to be c tau plus d to the minus k f of gamma z, or a tau plus b over c tau plus d. Okay, so I'll be using that a lot. All right, so a modular form, and hopefully this is somewhat familiar to most of you. So a modular form of weight k, multiplier nu on gamma is a function f from the upper half plane, the upper half of the complex plane, to C. satisfying three conditions, which I'll write on the next board. And actually, for right now, I actually want to just define. Let's define a weakly holomorphic modular form first, and then I'll talk about the usual modular forms in a minute. So it's going to satisfy three conditions. And the first one we've already talked about. The first one is that f/k gamma should be nu of gamma f for all gamma in gamma. And I wrote that slightly different than I had it before, but this number one says the same thing as this. Okay, so that's the fundamental relation that we need. But we also want a few other conditions. So number two is that f should be holomorphic or analytic on the upper half plane. And then the third one is that f is meromorphic at the cusps. I'll put that in quotes because I haven't defined what that means, and I'm going to explain what that means in a second. But these are the three properties. And when we talk about harmonic Maass forms, what we're going to do is talk about these three properties, and we're going to generalize number two and number three. Okay, so let me tell you what it means to be meromorphic at the cusps. All right, so for each gamma in SL2Z, so even if the group that we're looking at is a subgroup of SL2Z, for each gamma in SL2Z, the function f/k gamma is going to have a Fourier expansion that looks sort of like this. So f/k gamma will look like some n in Z, a n gamma q to the n over m, where m is an integer that could depend on gamma, and then these a n gammas, these are just the coefficients, and then meromorphic at the cusps. So 3 means it means that f/k gamma, well, this n is not allowed to go all the way to negative infinity. It's going to have to start at some point. So I'll indicate that by saying n is much larger than minus infinity. A n gamma q to the n over m. For every m, for every gamma in SL2Z. Okay. Maybe another way to say that instead of little m. No, so this little m, this could depend on, it could change depending on what gamma we put in. So this m, this is like, depending on which gamma we put in, this m, it's going to be the width of the cusp or something. So that will depend on gamma. Okay, another way to say this, so equivalently, we could say that for each gamma in SL2Z, there exists, let's say, a polynomial piece of gamma, and it's going to be a polynomial in q to the minus 1 over m. So this is a Laurent polynomial such that f slash k gamma minus e gamma. Let's see, what do I want to say about this? Yeah, that this function, that it decays exponentially, so e to the minus cv as v goes to infinity. Here, let's see, I don't think I've said this yet, but tau should be u plus iv everywhere. As v goes to infinity, this function should decay exponentially. So I'm thinking of p sub gamma as being the principal part of this function. So it's all the negative powers of q, and also the constant term if there is one. Okay, so we'll think of p as the principal part. Yeah, okay. And so now I can define all the spaces that I want. So I'll start with mk. Different people call this exclamation mark different things. So some people call it shriek, and some people call it bang, and you can just call it whatever you want. It's an exclamation mark. So this is the space of weakly holomorphic modular forms. And then sitting inside here is the space of, oh wow, I just really did not give myself enough room on that. It's a huge thing there. Is the space of modular forms. And these are the ones for which E gamma is allowed to only just be a constant. So basically this principal part, it basically doesn't exist. It's basically just a constant term. And then sitting inside there is the space of cusp forms. And these are the ones for which this principal part is actually just 0. So at every cusp, the function vanishes instead of has this this principal part. Okay, so these are the usual spaces. You happy with that? All right. I will probably not mention this multiplier system explicitly, and when I don't, I think I already said what the defaults are. So if the new doesn't show up in the definition, then that means it's just either the trivial character in integer weight, or it's this theta multiplier in half integer weight. Okay, so now let's talk about harmonic Maass forms. So what we're going to do is we're going to look at condition 2 for a minute. So I can rewrite condition 2. Condition 2 is equivalent to saying that d tau bar f is equal to 0. Okay, this is the Cauchy-Riemann equations. So d tau bar is the derivative with respect to tau bar, if you like. And this is saying that f is a function of tau and not a function of tau bar. Right? So f is holomorphic. Okay? Now the derivative doesn't play really nicely with the action of SL2Z, as we saw before. And so what I'm going to do is modify this slightly. So let's define an operator, which is called C sub k. And this is going to be the operator 2i v to the k d tau bar bar. Now, this is not the thing that it has to be. The 2i is a normalization factor. The conjugate here is going to make some things nice in a minute, but this v to the k is really the thing that's needed in order to make sure that that modularity isn't broken. Yes. That if F is holomorphic, then that. Yeah, so if you write down, let me just write down the definition of, yeah, so d tau bar is, I always get this wrong unless I look at it. 1/2 d du plus I d dv. And so the Cauchy-Riemann equations, like this is the Cauchy-Riemann equations. So yeah. Okay, so this operator, this Xi operator, this v to the k is here, so that the Xi operator plays nicely with the slash operator. So I'll tell you what that means. So Xi k of f, Xi k, okay, I'm gonna definitely mess this up if I don't look at it. F slash k gamma. So if I slash with something and then I take Xi of it, this is the same thing as taking Xi first and then slashing actually in weight 2 minus k. All right, and that we're going to see in a minute. Well, maybe sort of at the end, that really what's happening here is the derivative is this d tau bar is going to actually lower the weight by 2. So the d tau bar actually lowers the weight by 2. That's not obvious, but you can check that. And then the conjugation actually makes the weight negated. So this will take us to weight k minus 2, and then you conjugate and get to weight 2 minus k. And this v to the k just sort of makes this slash operator work nicely. So this seems like a nice operator. It plays nicely with the slash operator. And so we could actually rewrite 2 again, and we could say that this is equivalent to saying that CKF is equal to 0, because CK is just d tau bar with some decorations on it. Okay. But the Xi operator is also very nice for the following reason, and that's because it's essentially it's a part of the weight k hyperbolic Laplacian. So the weight k hyperbolic Laplacian. We've seen this already today in Professor Murty's talk. Weight k hyperbolic Laplacian is delta k. So this is minus y. Oh, I'm using y again. That's bad. That's v. I'm definitely going to mess that up again. So minus v squared, partial derivative with respect to u. These are second order. Okay, plus I k v, partial with respect to u, plus I partial with respect to v. And this is the Laplacian, but one really nice property of this Xi operator is that it basically factors the Laplacian. So if you do Xi k, and then you follow it up with C2 minus k, and then give it a little minus sign, you'll get exactly this operator. And that's a fun little exercise. And by fun, I mean it's actually not that fun at all, but you should do it at one point in your life. It makes sense that you'd want to do C2 minus k after Ck because of this, right? So it takes modular forms of weight k to things of weight 2 minus k. So that's the thing that makes sense to do. Okay, so we saw that number 2 was equivalent to being annihilated by this piece. That this piece annihilates modular forms. Well, what if we allow ourselves to not be annihilated by this one application of Xi, but actually by both of them? Okay, and that will be a nice generalization of number 2. So let's do that. Maybe what I'll do is just write that right over the top of this definition. I will just I'll just erase a few things, and we'll just fill in the things that change. Okay, so not a modular form, but a harmonic Maass form. Of weight k, multiplier nu on gamma is a function f from H to C satisfying three conditions. The first one is the same. The second one is different. And I'm also going to have to change the third one slightly. So let's do this. So the second one is now going to be replaced by F is annihilated by the weight K hyperbolic Laplacian. So this is just a direct generalization of what it used to say, because it used to say that F is annihilated by one application of the Cassie operator, and this is now saying that F is annihilated by two applications of the Cassie operator. Okay, so every modular form is going to satisfy this, but there are going to be more things now. And now I'm going to change number 3 slightly. So I will change it to say, so we needed a principal part a minute ago, and what I'm gonna say here is just that F slash K gamma. So we're looking at F at all of the cusps. That this all I really care is that this does not grow bigger than exponentially as V goes to infinity. And I'll play around with number 3 a little bit more as we move on, and we'll talk about other spaces as well. But this will be our sort of first definition. Okay, so this is a harmonic Maass form of weight K. And we'll say the space, the vector space of these is denoted, we'll call it HK shriek. And we'll have some distinguished subspaces of this as well. Okay, so this is a good place to pause for questions if there are any. Oh yeah, so this should say for every gamma in SL2Z. Because what we're really doing, all of these gammas are moving us to the different cusps. We're saying as we move to every cusp, F shouldn't grow more than exponentially at any cusp. Okay. Oh, just some constant. Yeah, I just positive constant. Yeah, some. Yeah, yeah. So for some, yeah, we'll just say for some positive constant. It could, though. It's not too hard to show. So since this gamma is going to have finite index in SL2Z, this is really only finitely many things, and you could just take C to be the maximum if you want. So yeah, but yeah, it could depend on gamma for sure. Okay. So let's talk about the Fourier expansion now. Okay. This is going to come from the fact. Okay, so by number 1, if we plug in gamma is say 1, 1, 0, 1. Then that's going to give us the Fourier expansion. So of course, this is going to have to be in the group, but in the 2 groups that I said we care about, which is gamma 0n and gamma 1n, that's in both of those groups. So if I plug in that into the Fourier expansion, then I get f of tau plus 1 equals f of tau. Okay, well, maybe there's a multiplier system, and maybe there's actually something here. For now, I'm going to just assume that the multiplier system is trivial on this element. It won't be if the multiplier system is, for example, the eta multiplier, but it's not too hard to fix this in that case. So I'm just going to work in this case. So because f is periodic of period 1, it's going to have a Fourier expansion that looks like sum n in z. Let's say a n v e of n u. And this notation here is going to come up a lot. So we'll say e of x is e to the 2 pi I x. And that's a standard abbreviation there. So F is going to have to be real analytic. I think because, let's see. Do I need to assume that? It's probably not assumed by, probably not implied by those. So let's say, yeah, let's say it has to be real analytic. It certainly has to be at least twice differentiable in order for this to even make sense. So that's a good point. So let's say it's real analytic, and then that will just cover things. Okay, so F has this Fourier expansion, and that just comes from this number one with this one matrix. So now let's impose the condition that number two tells us. So number two is going to imply some kind of differential equation that is satisfied by A and V, these coefficients, okay? So I'm not going to do this in all the gory detail, but this is not too hard to check. Let's do this in the case when n is 0 and then when n is not 0. So if I have delta k A0V equals 0, that's going to give me a differential equation that's satisfied by A0V. And it's going to be minus V squared. This one is quite easy to check. Second derivative of A0V minus KV, first derivative of A0V equals 0. Okay, and it's not too hard to find two linearly independent solutions to this. And so we can see pretty quickly that A0V is a linear combination of 1. Well, that's easy to see. And then also V to the, let's see, V to the 1 minus K. And it's not hard to check that those are both solutions to this differential equation. Okay? And then maybe the more interesting thing is what happens when n is not 0. And this one is a little bit more painful to actually work out, but it's not too bad. If n is not 0, let's write A and V as some function h of 2 pi nv. It's not clear from the outset that you should even be able to do that, but sort of after you do this calculation, you'll see that this is really sort of the right thing. Then h of y satisfies the following differential equation: h double prime plus k over y h prime plus h minus h is equal to 0. Which is probably everybody's favorite second order differential equation. You probably just know the things, right? So y, I'm thinking of y as sort of like all of this, right? I'm just thinking of this as just h of y, yeah. Yeah, so this is the one case I didn't actually mess up. Y actually isn't to be in this case. Okay, there are two linearly independent solutions. So H has two linearly independent solutions, which are e to the minus y and gamma of 1 minus k minus 2y e to the minus y. And I should tell you what gamma is, though we did see it in Professor Murty's talk. Gamma of s comma x. So this is the incomplete gamma function, the integral from x to infinity of e to the minus t, t to the s, dt over t. And I think we want real s to be bigger than 0 for this integral to converge, though this function has an analytic continuation to the whole complex plane. So it just isn't defined like that if the real s is negative. Okay, and then it's important to think about how big this thing is, how it grows. So gamma Sx is asymptotic to x to the s minus 1, e to the minus x, as absolute value of x goes to infinity. And so it's not too hard to check that. Okay, so this sum is now going to sort of split into two sums based on which solution we use. So maybe a sum that involves these and a sum that involves these. And based on these, based on this asymptotic, what it's basically saying is that on the e to the minus y side, we can't have the ends be all the way to negative infinity. And on the gamma side, we can't have all the ends be all the way to positive infinity. So I'm going to write that down, but that's sort of the idea, sort of what's going to happen. Otherwise, condition 3 wouldn't hold. So if k is not equal to 1, you're right. Good point. Let's not talk about k equal to 1 ever. Yeah, no, k equals 1 is just a weird case that like everything breaks. If we use this definition. If we use the analytic continuation of this, we can allow k to be anything we want. Yeah. But yeah, let's right now and forever just say k is not 1. And then we don't have to worry about that. Yeah, when k is 1, there are lots of interesting things that happen, but it's really just a case that just is very different in lots of ways. So, and it's a lot of it is because of this k to 2 minus k. Well, when k is 1, it doesn't do much, right? So there's really very different behavior. Okay, so if we take this this asymptotic and then we plug this into 3, what we get is that f of tau has to look like this. So it has to have the part that uses e to the minus y. So this is going to be, let's call this a plus of n, q to the n. And all of the n's, they can't go all the way to negative infinity. Okay, they have to start at some negative number, and then they can go all the way to positive infinity. And then there's going to be some, let's see this, well, we need the constant term, which is going to involve this v to the 1 minus k. So we'll call this a minus of 0, v to the 1 minus k. And then a sum, which is not allowed to go all the way to plus infinity, a minus of n, gamma of 1 minus k, minus 4 pi n v, q to the minus n. Sorry, q to the n. Okay? And this splits nicely into really two distinct parts. And this is what we call the holomorphic part. Since it really just is a function of q, this is a holomorphic function. And then we will call this the non-holomorphic part. Okay? So if, now this is a direct generalization of modular forms. And so if f is a modular form, it automatically satisfies 2. And so modular forms are, of course, going to just have the holomorphic part and not the non-holomorphic part. This allows us to have something more general. So, and I should point out, let's see, so this has exponential growth for negative n, which is why we can't let n go all the way to negative infinity. And this part has exponential growth or positive n, which is why we can't let n go all the way to positive infinity on that side. Sorry, what? Oh, yeah, so this is just the Fourier expansion at infinity. I'm not thinking of all of the other gammas. I'm really just taking gamma to be the identity matrix here. Though F will have an expansion like this at every cusp. Maybe slightly more complicated depending on the multiplier system, but something analogous is going to happen as well. Yeah. Did that answer your question? Okay. Okay. So I'd like to classify harmonic Maass forms based on the behavior of these two parts, based on the behavior of the holomorphic and non-holomorphic parts. And this is going to play into something related, which is called the shadow of F. And this is going to be CK of F. And I'm just going to call this G for now, so that I can refer to it several times. But I'm going to classify harmonic Maass forms based on the behavior of the shadow and also the holomorphic part of F. Okay, so remember that delta K F is 0. But delta K F is the same thing as minus C2 minus K CK F. So if this is G, the shadow, then number 2 implies that G is holomorphic of weight 2 minus K. Okay, so it's a weakly holomorphic modular form of weight 2 minus K. And so we're going to think about the different options for G and then classify harmonic Maass forms based on that. Now, I do want to point out one thing with the multiplier system. So if I have that F slash K gamma is nu of gamma F, then this implies that CKF slash 2 minus K gamma is, well, because the C operator has a complex conjugate in it, this is going to spit out a new bar of gamma CKF. So G is holomorphic of weight 2 minus K for multiplier system nu bar, which probably isn't going to come into play too much, but I just wanted to point that out. Okay, so let's start with this space HK shriek of gamma, if you like. So these are all the harmonic Maass forms, and there's no condition on these based on the shadow or the holomorphic part. But what I want to go is I want to go in two directions here. So, and I'm going to define a subspace HK. This is a sharp gamma. I didn't make the notation, but that's the standard thing, is to put a sharp here. And this will have growth only in the non-holomorphic part. Or in other words, that means that n has to be greater than or equal to 0 in the holomorphic part. So there are no negative n's allowed in the summation in the holomorphic part. Okay? And then we'll also define HK gamma with no sharp, no exclamation point. These were sort of the first ones studied, and so they get the special treatment of not having any decorations. And this allows for growth only in the holomorphic part. Or in other words, n has to be strictly negative in the non-holomorphic part. And there's not going to be any constant term. So what does this mean for the shadow? So here the shadow has to be a cusp form for gamma. Because if you apply the Cassie operator, and maybe we'll talk about this in a few minutes, but if you apply the Cassie operator to something like this, what it does is it basically takes all of these, it takes these terms here, and it replaces these by q to the minus n. And so it basically takes all the negative n's and turns them into positive n's. And so in order for f, or in order for g to satisfy that, it's going to have to be a cusp form. And here, because the growth happens in the non-holomorphic part, G is going to have to be a weakly holomorphic modular form that isn't a cusp form. So it can be a holomorphic modular form like an Eisenstein series, or it can be weakly holomorphic, but not a cusp form. Okay. And so that will split this into sort of two distinct pieces that I'm sure will come up in later lectures. Okay, I only have a few minutes left. I have a few more things to say, but are there any questions at this point? Yes. If it's in the kernel of C2 minus K, is it in the image of CK? Should be, right? Yeah, I think so, yes. So what that? Yes, and I'm actually going to write down an exact sequence in a second. Okay, so yeah, let me just say a couple of things. Yeah, that was sort of the next thing on my list, actually. Yeah, okay, so let me say one thing about the shadow. So we can also write F. So we can take its holomorphic part, and I'll just call that F plus. So this is the holomorphic part. And we can write this, I'm just going to put a star here for, there's some constant that I'm not going to write down. We can write this like, sort of like an Eichler integral, if you're familiar with that. It's an integral from minus tau bar to I infinity of g of z, not quite g of z, I'll call it gc of z, over minus I z plus tau to the k dz. Where this gc of z is just, you just conjugate the coefficients of g. So it's just exactly g, but you just take the conjugate of all the coefficients. And if I had time, I was going to actually work this out, but I don't think I'm going to. But this is a nice little calculation, and it really shows where the shadow plays a really important part here. Is that it just shows up as the numerator of this integrand in this integral. So we can think of the non-holomorphic part as sort of a non-holomorphic Eichler integral of a weakly holomorphic modular form. Okay, I want to just say a couple of words of some theorems of Bruinier and Funke, and then I'll be done. Okay, theorem. So this theorem shows up in a landmark paper of Bruinier and Funke from the early 2000s. And this paper really did a lot for the theory of harmonic Maass forms. So let's suppose k is not equal to 1 still, and also gamma is 0 of n. There is a generalization of this to other groups, but I'm just going to write down this version. Then the maps ck from hk gamma to s2 minus k gamma, and ck from hk shriek gamma to weakly holomorphic modular forms. Both of these maps are surjective. So in other words, if you have a favorite cusp form, then there does exist a harmonic Maass form whose shadow is your favorite cusp form. And same is true for weakly holomorphic forms. The proof that appears in Bruinier and Funke is geometric, and it's very nice. There's another proof that uses the theory of Poincare series. And since that's one of the subjects of my next talk tomorrow, I think I'll just mention, when I talk about Poincare series, I will just sort of mention how you might write down a proof of this once you've worked out various facts about Poincare series. Okay, so I'll just end by telling you about two other differential operators that come up, and then I'll be done. So here are two other operators. And they might come up this week at some point. So these are called the Maass lowering operator and the Maass raising operator. And they're called that because they lower and raise the weight. So pretty simple. So the lowering operator is called LK, and it looks a lot like the C operator, except it does not involve a conjugate over the whole thing. So this is minus 2i v squared d tau bar. And then the raising operator is 2i d tau plus k over v. And basically these have the following properties. So the lowering operator takes you from weight k to weight k minus 2. And the raising operator takes you from weight k to weight k plus 2. Though these do not preserve the eigenvalue of the Laplacian. So for us, for harmonic Maass forms, the eigenvalue of the Laplacian is 0. But actually, these both mess with the eigenvalue of the Laplacian. And so neither of these operators preserves spaces of harmonic Maass forms, though they do act on spaces of more general Maass forms of general eigenvalues with a specified action on the eigenvalue. In fact, I could write it down. I'm not going to. It doesn't really matter. And then maybe one last thing to say is that if you put these together, minus the Laplacian is, well, it's lowering first and then raising. So lowering in weight k and then raising in weight k minus 2. So if you lower and then raise, then you get the Laplacian. So these might come up, but they're not going to come up in this talk because this talk is done. So Thank you, and that's it.
Thank you. My first question, say the holomorphic case, algebra acts on the right hand side.
Yeah.
And your map is say somehow introduce some equality among the harmonic mass form because of subjective.
Yeah.
Therefore, it should be expected there should be an infinite dimension of algebra like this. Similar kind of should holds good Hecke algebra. The case of
Yeah, so the Hecke algebra does act on harmonic Maass forms in a nice way. And I believe Michael will be talking about that in a future talk. Not today, though, right? Not today. Yeah. So I'm going to defer the answer to that question to him for a different day. Yeah.
Any other question, remark?
Yes.
Zwegers thought that the shadow name was given by him, but do you know why?
Yeah, so Zwegers did call it a shadow first. And maybe I'm being a little bit historically inaccurate in calling G the shadow of F. Because to Zwegers, the shadow was really a thing that is associated to F plus, the harmonic or the holomorphic part, which is called a Mach modular form. And so to him, he was thinking, okay, this Mach modular form, there's this thing sort of hiding. There's a shadow, it's sort of hiding. You can't see it. But if you include it in this way, right? If you take your Mach modular form and you include the shadow, which is sort of hiding, then you get something that transforms. And so to Zwegers, the shadow, G is the shadow of F plus, not the shadow of F. Though I think most people at this point just sort of say it's the shadow of F. Yeah. But historically, that's how it came up. Yeah. Oh, yes, this only, yes, I didn't mention that, but this only works, here in this second case and not in the first case. Thank you. Yeah.
And the